right, everybody. I think I'm going to go ahead and get started. We're supposed to have about 35 people here, so I don't quite have that many yet, but it might take a few minutes to get everybody in here. So that's okay. We'll sort of start slow here. First of all, welcome to Math 250B, and thank you for being here. I'm glad that you've been paying attention to your emails and finding your way over in Zoom this week and next week, these first 2 weeks. I am not in California right now. In fact, I haven't been in California since the middle of December. I went out of the area for some holiday time, and I'll tell you in a minute where I'm at and what's going on with me. First of all, I hope everything that's going on with you guys is all going well. I know that, well, I've seen the news, even though I haven't been in Southern California. I know there's been a lot going on with fires, and I hope that all of you have been staying safe and staying out of harm's way, both you, your family, and your property and everything else. Gosh, it's just amazing what I've been seeing on the news. But my understanding is it's been a little bit away from Fullerton, but I know I have at least one colleague who I know who has been affected by this pretty dramatically. So I hope that that hasn't been the case for you guys. I hope you all are doing really, really great. Yeah, so what's going on with me is that, well, I came home for the holidays. I am here at my parents' house. My parents are getting a little older. My mom had a hip surgery about 2 months ago, and my dad, almost at the same time, had to have a knee surgery. And I came back for the holidays, and it was pretty clear that they could use a little extra help while they're recovering from that. It's kind of a slow process. I think they're coming along really well, but doctor sort of said, "Yeah, it'd be great if somebody could be around to help for a couple extra weeks into the new year." So I asked my department. I said, "Yeah, if you want to sort of start off for a couple weeks in Zoom, I think that'd be okay." So I hope it's okay with you guys as well. I think it's good for my folks to have a little extra help and support here. But I am coming back soon. It will not be long that we are doing this Zoom thing. I am coming back to SoCal the first weekend in February, right at the start of February, I believe it is, that very first couple of days. And so 2 weeks from now, we'll already be able to meet again in person, face to face. My parents' house is actually in Nebraska. So I don't know if you've ever talked to anybody in Nebraska before, but if you take the map of the United States and you point straight into the center of it, that's basically where I am. It's about 20 degrees outside. The wind has been blowing like crazy. It's really cold here, but luckily no fires here. But it's other than that, other than the temperatures, I'm kind of dealing with the same dry weather that you guys are. It's about 50 degrees colder, I have a feeling, where I am. So that's why I've got the sweater on. I'm down here in the basement of my parents' house. This is where I was teaching during COVID too. So it's sort of deja vu for me, kind of going back to that. And yeah, so I just want to thank you guys for your patience with me here at the start of the semester. I am really excited about Math 250B. I've taught it more than 30 times. I've taught it more than anybody else at Cal State Fullerton, and I would venture to say I've probably taught it more than anybody else in Southern California. It would be hard to imagine because I teach it every semester and I get 35, 40 students, 2 sections every semester for the last 20 years pretty much. So I kind of got this drilled down. I realized the other day that I had forgotten my lecture notes out at my office in California. And I said, "Oh, that's okay. I can just scribble down some sketch of some notes and I should be fine." I can almost hear myself going over the material from 6 months ago and almost just spit out those same words again, and it should come out just about perfect. At least that's what I'm hoping. We'll see. We'll see how it goes. Like I said, I am going to be back very soon. So just a little over a week from now, I'll be back in Southern California. Thank you very much, though, for watching those videos for me while I was gone to kind of make sure we don't fall behind. I hate getting behind, especially right at the start of the semester. It's kind of not when you want to sort of get off on a bad foot. So I had a chance this morning to go through those notes. I made a few comments. Occasionally somebody, didn't scan things quite right. I had some trouble reading some papers, but it was a good chance for me to kind of bring your attention to that, so that maybe before we get into the real homework of the semester, you guys can kind of work on the submission process. Remember, I only want to get one file. I don't mind if you submit something and then overwrite it with a new, if you decide that you're not happy with what you turned in and you want to turn in a better version of your homework, as long as it's before the deadline, I don't mind that at all. But make sure it's just one file, please. If you need to download an app to scan several pages together, please do that, because it's just a hassle to have to constantly click and open a bunch of pages. So I would rather have just one file. Other than that, for the most part, it was a pretty good set of papers with those video notes. There was an occasional, I could see a couple people didn't quite get it done in time, but we got time. We'll get this stuff all done. I think we should be fine. In terms of, I have a few more announcements here, guys. Since it's kind of our first live meeting, I just want to make sure I go over a few things. I wanted to make sure everybody knows there is a homework assignment due tomorrow night, and it's due at midnight tomorrow night. I have office hours today after class, so as soon as we're done with class, I'm going to probably 10 minutes later, I'll show up in my Zoom office instead of this room. This is actually the Zoom classroom. So I'll be showing up in my Zoom office shortly after class tonight, and I'll be around all evening. And you can certainly chat with me over there in my Zoom office about the homework that's due tomorrow night. I'm also going to have some hours tomorrow. Oh, but what I forgot to tell you guys is that Nebraska is 2 hours later than California. It is already 8 p.m. right here. And by the time we're done with this class, it's going to be 10 p.m. And that's no problem, because I'm a night owl. And so I'm going to stay up for these office hours this evening, starting at what is 8 p.m. for you, but what is 10 p.m. for me. And I'm going to stay up past midnight tonight having office hours, just because I feel like I want to do that. However, I also have some hours tomorrow on Friday, because that's the day the homework is due. And I looked at those hours and I realized that with the 2-hour time shift, my office hours are going to land me right in the middle of dinner with my parents if I stick with those. So I'm going to make a slight change. You might want to jot this down. This is just for tomorrow. So tomorrow, which is Friday, my office hours, I'm going to just do, and this is California time, I'm just going to do 7 to 10 p.m. This is going to work great for me. It'll be after my dinner time with my family, but before it gets too late. So just for tomorrow, just jot that down in case you're working on the homework and you've got some questions for me. I'll certainly be glad to talk to you tomorrow. You can also shoot me an email. I've had a few people emailing me with some questions. If you want to chat with me that way and reach out, feel free to do that as well. I'll do whatever I can to help you out. We are going to have a lot of homework in this class. 24 assignments to be exact. I already know the exact number. That's not quite 2 assignments per week, but it's more than 1 per week normally. So the first homework is due tomorrow night. The next one will be due on Tuesday. Next week on Tuesday, and then the third one will be due next week on Friday. So Tuesday, Friday, I'm kind of going along with that pattern, at least to start off with. But if you really want to know when all the homework assignments are due, just check the Canvas assignments page. And I have, I think, the first 8 assignments already published. So if you want to get a head start, you certainly can do that. I'm going to also try to take some questions on tomorrow's homework during class tonight. If you have any, you can throw them in the chat. Maybe I'll tell you a little bit later when you can throw those in the chat. This is a 2-hour class, and that's a long time to sit and listen to me talk. Normally during class, I'm going to be doing group work activities at least once a week, where you guys are going to get up and work on problems together. We're not going to do that so much this week, obviously. And the other thing is we will always take a 10-minute break in the middle of class, roughly in the middle of class. So you're not going to have to sit there looking at the screen for 2 hours. I will give you a chance to get up and take a break. I get really excited. You're going to see that starting in the 3rd week. I like to run around my whiteboards, and I love talking about this stuff. It's a little harder when I'm kind of stuck here with this whiteboard, but I insisted on setting up a little studio down here with whiteboards rather than just teaching off of an iPad, which I know some of my colleagues like to do. I don't like to do that. I like to have my face up in front of everybody and working kind of real time live on a whiteboard, kind of in the classic traditional style. So that's what we'll do. I'll try to keep you guys awake. I know it's a little late in the evening for this class, but I'm hoping that that'll be okay. By the way, I hope everybody's been able to get a hold of the textbook. I have like 5 or 6 copies of the book in my office, but the problem is I'm not there right now. So once I'm back, you'll be able to borrow a book from me anytime you like. In the meantime, I did post the homework sets or the homework problems from the first 3 assignments into Canvas. There's a folder that's in the file section. I think it's called Chapter 1 Homework Problems. And so if you don't have the book and you're like, well, how do I get a hold of the questions I'm supposed to do for the homework? You should be able to find those questions in Canvas now. And if you have any questions about it, you can ask me and I'll help you out. Okay, couple more things. One is that there is also an SI section that is associated with this class. And our SI leader is actually here right now. I'm not going to embarrass her too much, but Audrey took this class from me very recently, and you could not be in better hands with anybody else. She really knows this material well. She knows how I teach it. She's pretty fresh with the material because she's done this very recently. The SI session is, of course, optional. You don't have to register for this, but many students may find it helpful. It's being offered on Tuesdays and Thursdays at 4 o'clock, so it's before this class. And if you're interested in signing up for that, be sure to let me know, or you can send Audrey a note. She's in the room right now. I'll probably
Dr. And I can
Yeah.
say something if you want me to, just so you don't have to try to remember everything. But I don't want to interrupt also,
yeah.
so let me know.
Feel free. Why don't you let everybody know what your thoughts are about the SI session?
Sounds good. Yeah, I'll just take a second. But you guys are in great hands with Dr. Annan. I'm very happy for you. You're very fortunate. I've met some of you, I think a couple of you. I'm Audrey. I'm an electrical engineering major. I did take this class really recently, and again, Dr. Annan's the best. It's a lot of work, but if you don't understand something, he will do everything he can to help you with that. SI is about group work, and we're collaborating together. It's kind of like a study workshop. Some of you have been already, but it's really a great chance for you to reinforce the concepts from this class because there's so many topics. So just hearing them and then writing them down isn't going to stick in your brain as well as discussing with other people, being on whiteboards. That really helped me when I was in this class too. So I highly recommend you come. One thing is that up to 16 students are allowed to be enrolled, and then you get a credit for that. Right now we are at max capacity, but it's still the first week. And so I just want to encourage you to keep checking that, even go on the wait list, because in the first week, a lot of people are going to drop and decide, oh no, this isn't a good fit. But I would really love to have you there.
All right. Yeah, thank you, Audrey. Really appreciate that. I think even if you didn't want to register, if there's space in her SI session, she doesn't mind if people just drop by. So you can also just do that, but just knowing that if the room is full, she may not be able to accommodate everybody going. I do have 2 sessions of 250B, and they're both completely full. So I have about 70 students as of right now. Actually, that brings me to another thing I wanted to mention. The waiting list for this class. Most people are already enrolled, but there are a couple of people on the waiting list. I cannot do anything about that this week. This week, the only way that the waiting list works is just with the online waiting list that you can put your name onto. Hopefully you're all mostly in the class by now. If you're still on the waiting list, try to hang in there. Next week, I'm able to add people. I actually then at that point have the power to add somebody into the class. The only issue with that is that I can get overruled by the department if they come back and tell me, oh, you don't have enough chairs in your classroom to take extra people. So that can be an issue, but I am fairly optimistic. Cody, I think you might have been on the waiting list, and there might have been one other person. Maybe it was Bryant. I can't quite remember off the top of my head. Anyway, hang in there. Of course, if it was up to me and I was in control of everything, I would just add everybody without any problem. But in this case, I can't do that. The classroom has a certain number of chairs in it, and we have to kind of go with that. So, I think there's a good chance that there'll be a space opening up. I gave you guys quite a bit of videos to watch on purpose to kind of see who's really serious here and going to stick with it. And a couple of people have already kind of decided that they don't have enough time for this. And there may be a few more who do that. Guys, this is a 4-unit class, and it is going to feel every bit of that. A lot of schools will teach differential equations and linear algebra as 2 separate courses. Our university does what I like the best, which is it integrates the 2 subjects together, right? If you just took a straight linear algebra class, especially if you're an engineer, if you took a straight linear algebra class, you would spend a lot of time sitting there feeling like this is really abstract and theoretical, and I don't know what it's good for, right? And if you took a straight differential equations class, you would be a little bit unsatisfied about the fact that halfway through the semester, the professor would suddenly stop talking about differential equations for a month because, well, there's this thing called determinants and vector spaces that we have to go over. And so that also would feel a little awkward. Well, we're not going to try to hide that connection. We're going to really try to blend these 2 subjects together. But that does mean that there's a lot to this class. There's a lot that we're going to cover, and it really helps that you guys watched those videos to kind of get us off to a good start. But yeah, just keep in mind it's gonna keep you busy as we go along here. Okay, so I think those are the most of the announcements I wanted to make. Does anybody have any questions? I should point out, you might notice that there's 2 of me in this room. That's because I logged on both with my laptop and with my phone. And I have my chat box open. If you want to send a chat, that's great, but please send it to everyone. Don't send it to me privately, because if you send it to me privately on my phone, I might not see it, or my laptop, I might not see it depending on which one I'm looking at. So also, it's good for everybody to see everything that's going through the chat. So feel free to ask questions in the chat. You're also welcome to do what Audrey just did, which is to just unmute yourself and just ask a question, get my attention. Sometimes I get a little excited about this stuff and I lose track that somebody might have a question out there. And it's good if I kind of get put in check on that. So feel free to use your microphone to get my attention, okay? But does anybody have any questions about anything I've sort of said up until now? Appreciate all the webcams. I know not everyone can do it, but those of you who have those on, it's really, really helpful for me to kind of see some faces and get an idea that at least I'm saying something that hopefully is making a little bit of sense to some of you out there. Guys, I will almost always start my classes with a summary, or what I like to call a recap of what we would have been covering in the previous class. It's always a good idea for you guys to kind of skim through your notes before you come into class, if that's possible. I think if you were in the SI session, you'd already kind of be freshening yourself up before class with the material. But in case you're not, it's not a bad idea to just kind of glance through your notes so you're not just coming in cold, especially at the start of a new week. You might not have been thinking about the material for 4 or 5 days. It's really you're gonna get more out of my class if you've actually kind of reviewed a little bit and come in. But I'm gonna help with that by doing these little recaps. And in this case, what I have is kind of what I've called a video recap. I had you watching a lot of videos up until this past Tuesday, and I've summarized some, not all, but some of the key points from some of those videos up here. And I always recommend jotting these down, or at least you can take a picture of it if you'd rather. Um, just because it is kind of a nice summary, I think, of what we've done. Obviously, as you know, we're kind of starting from chapter 1 at the beginning, and that's all about first order differential equations. So the order of a differential equation, right? That's just the maximum number of derivatives that you see in the equation anywhere. And so first order equations, they will have just the first derivative of the unknown function in them, nothing higher than that. And we talked in the videos about two of the premier types of differential equations, and they are the separable ones and the linear ones. Okay, the good news here is that a large share of the important differential equations for physics, for engineering, for chemistry, a lot of the differential equations that are important are either separable or linear. And so if we know how to solve these equations, we've already got a really nice start on things. And so that's why I wanted you to kind of get familiar with this right off the bat. Remember that a separable equation, I'm just going to review this recap for a minute, if you guys are good with that. A separable equation just literally is what the word means. I'm going to separate the two variables, the x's and the y's, onto opposite sides of an equal sign, right? So I can't always do that. It won't always be set up for me like that. And so sometimes there's some algebra that comes into separating the equation. In the videos, when I did some examples of this, you would have seen that, right? You would have seen me doing some algebra to get all of the x's onto one side, all of the y's onto the other side. But once we've done that, once we've, if it's possible, and if we've managed to get the equation separated, as I've indicated here, then the method for solving these equations is to simply integrate on both sides. Okay, so pretty straightforward. We just have to integrate both sides of that equation. And if possible, we would then try to solve for y. That's the unknown function that we're really solving for. Sometimes you can't do that and you're just willing to settle for an implicit solution to your differential equation. But if possible, after we integrate both sides, we can clean it up a little bit and maybe isolate the y. That's kind of the ideal form to get the answer into. I had an example. I asked you to watch another video that was about Newton's law of cooling. That's a great example of a separable differential equation. Okay, so it's kind of in the realm of physics here a little bit. I do want to note that in the notes, there should be a minus sign. I kind of extracted that negative sign in the video where I was talking about this equation. And when I went over everybody's notes, I kind of skimmed through the notes that you guys took on that lecture. There were a handful of people that had just lost the minus sign, and no big deal, but just make sure. I tried to write a comment in my feedback for you on your notes if I noticed a sign error there, but that should have a minus sign on it. And yeah, that is solved by separating the variables. In this case, it's the little t and the big T. Those are the variables. It's not x and y. But you can separate that differential equation and then solve it by integrating both sides. And I did that for you in one of the videos that you've watched. Okay, so the solution to this differential equation is something that you should already have in your notes. I won't write it down for now, but it's just nice to have an application. Okay. So those are the separable differential equations, and very, very common, very, very standard, very, very standard process to solve those. Right. Shortly thereafter, I had another video about linear differential equations that I had you guys watch as well. This one is just one step up in terms of the complexity of it, but still pretty straightforward, very common again. It has this form that I've put in this box here. By the way, anything that's in a box is probably something you're going to want start trying to learn a little bit. So the equation would look like this: y prime plus some function p of x times y. And on the right-hand side, it's equal to q of x, right? So this is the form of a linear differential equation. And in this case, the method that is traditionally used to solve this is to introduce this so-called integrating factor. And again, I derived this in detail in the notes you've already taken. But I did want to get the formula back up here again. I of x equals e raised to the power. Is everybody able to read this? This is e raised to the power of the integral of p of x dx. Okay, if you ever have trouble reading anything on my board, guys, just holler, okay? Because I realize that there's a chance that something could get lost in transmission here. But this is an exponent, e to the exponent of the integral of p of x dx, right? So we have to work out that integrating factor. And then I'm not going to go through all of the details here, but what ultimately you end up doing is you get the derivative of the product of the integrating factor with the unknown function y on the left side. And at the same time, on the right side, you end up getting q of x times I, right? And the goal is to solve for y. That's my unknown function. And once you've written this down, which you can literally just copy down once you know the integrating factor, well, now you just have to integrate both sides and then divide by I in order to isolate y. So you should be able to explicitly solve this one for y. That's right. Okay, and a nice real world application of this type of differential equation. I put it over here. It's the mixing problems. So you have a tank with some chemicals in it, and the solution is changing as a function of time as you're pouring chemicals in and they're leaking out. I won't go over what all of these variables mean again right now, the R1, the C1, the R2. This was all covered in the videos that you watched. But I just wanted to kind of get it in front of you one more time so you can make the connection. This second row here of my table is all about linear differential equations, and then the mixing problems is a nice application of it. I always like to try to give you a reason to care about anything we're learning here. And so applications are good. I know many of you are engineering students. And so unlike myself, where I can be entertained with just the theoretical background of the math itself, I know many of you want to know that this stuff is actually useful and that we can actually put this to a good application. So I've got a couple of those over there for you. Does anybody have any questions about what's up here so far on my boards? This is sort of just a video recap. Is it all looking pretty familiar? Seem reasonable? Thanks, Aiden. Yeah, if you want to, you can use the reaction tools in Zoom, or you can just wave at me or something if you're feeling pretty good, or you can look not so happy if you're not feeling so good. It's whatever the appropriate reaction is. Okay. Well, to tell you guys the truth, I could spend 15 weeks doing this. I could spend the entire semester introducing another kind of differential equation, writing down a method for how to solve it, and trying to give you an application of it. And I could do this over and over and over, rinse and repeat for 15 weeks. We could just do that. It would be a very, very dry version of a differential equations class. My guess is there would be a lot of memorizing. There would be not a lot of retention. It would be a rather monotonous and pedestrian thing to sort of engage in for 15 weeks. So we've learned a couple of kinds of differential equations here, but I want to aim a little bit higher than just kind of giving you some kind of an infinite library of differential equations, right? Because at some point you sort of get bored with it and you're like, yeah, okay, I've seen this kind of thing before. So what I'm going to do is aim a little bit higher and try to focus more on what are some of the powerful tools that we can use that will help us just get better at differential equations in general. right? What are some of the big things we can do? Well, one of them is, well, the biggest one of all is going to be linear algebra, which, by the way, we're already going to be getting into next week, okay? So linear algebra is going to be a huge tool. Before we get into the linear algebra, though, I want to give you a slightly milder tool, just to give you the flavor of this. And it is something called change of variables. So I'm going to go ahead and start writing some new things on my board now. And you'll have to forgive me. I'm down here in the basement of my parents' house, and they don't turn the heat up very well in here. I don't know. Do you guys know that if you are in a room that's like 50 degrees or colder, and you try to start writing on a whiteboard, you won't be able to erase it? Didn't know this until I started teaching during COVID. I was out in the garage of my house in Colorado, and I had all these notes on the board. And it was freezing. It was like wintertime temperatures, probably like 20 degrees or something. And I started trying to erase it. I could not erase the board to save my life. And so I went and got a space heater, and I put it about 5 feet away from the board and started blowing hot air, blasting hot air onto the board to try to warm it up. And yeah, that actually does work. As soon as you get the board warmed up, it'll erase it like nothing else. So this room is not quite as cold as that garage was, so I am able to erase it, but it's a little bit difficult. I'm just doing the best I can. I really want to use a whiteboard rather than an iPad to show you guys this stuff. So anyway, but I have a little bit of room here to get started. And so we're going to take a look at a very powerful tool in the theory of differential equations. This is in section 1.8, and this is called change of variables. And this is not anything totally foreign to you. Back when you were learning how to do integration in your calculus classes, one of the first techniques that they probably showed you was something called U substitution. When you do an integral by U substitution, you are changing variables. You are taking the integral that is in front of you, which is maybe difficult to think about how to solve, and you are changing the variables. You are doing a U substitution, which converts it, hopefully, into something easier to solve. Well, differential equations specialists have figured out that same kind of idea can be helpful for solving differential equations as well. And I'd like to show you 2 examples of this. So I'm gonna label these with sort of 2 sections here, A and B. And the first one is I'm going to talk about something called a Bernoulli differential equation. Okay, and then once I'm done with that, I'm going to do a second little mini lecture on something called a homogeneous differential equation of degree 0. So by the end of tonight's class, you guys are going to know how to solve not just separable and linear differential equations, but hopefully also the Bernoulli and homogeneous differential equations. These are solved by changing variables. And the first thing I'm just going to give you a little sneak peek at what is going to happen when we apply this change of variables. Guys, these Bernoulli equations, which I'll explain in just a moment, they always get converted through this change of variables process. They always become linear. They always become linear, as it turns out. Okay. And then the homogeneous differential equations of degree 0, those always become separable. So there you go. We can start with a Bernoulli or a homogeneous differential equation, and through the change of variables that I'm about to describe, we can turn it into a separable one. Okay, so that's the preview of what we're going to do here in the next minutes ahead of us. I'm going to start here. I think I have room to get started right here on the bottom of this board. I'm going to make, in section A, I'm going to give you the definition. DEFN stands for definition. I'm going to give you the definition right now of a Bernoulli differential equation. So a Bernoulli differential equation, and I'll underline the word that I'm defining. That's sort of my standard way of doing this. A Bernoulli differential equation has the form, and now I'm going to write it down for you. It is going to look like this: y prime plus p of x times y equals, and I actually want to stop for just a second. Will you notice so far what I've written on the left side is exactly the same as what's on the left side of the linear equations that we've already talked about in the past. So somehow these Bernoulli equations are very similar to the linear ones. So on the right-hand side, we are going to have the q of x that we've already seen before, but this is multiplied now by y to the n. Okay, that very last part, that y to the n, is what makes this different. If I have like a y squared or a y cubed or a y to the fourth, that destroys the linear nature of it, right? Your differential equation, we talked about this in the videos, right? A linear differential equation cannot have a y squared in it, cannot have a y cubed in it, or anything like that. So if I have a power of y on the right-hand side here, this is no longer linear, but it's close to being linear. We can see the only difference is the y to the n. And so indeed, what I'm going to do, guys, is I'm going to try to change the variables to turn this Bernoulli equation into a linear one. Okay, so how do we do this? So let me come over here, and I'm now going to talk about how we're actually going to solve this. Okay, so to solve this, this is where the powerful technique of change of variables is actually going to come in. So to solve this, we are going to use the change of variables. And I'm going to give you the formula for it, and you are going to want to memorize this. Okay, so the formula for this is u equals y raised to the power of 1 minus n. I'll put that in a box just to really emphasize that. So the n that you see there is the same n that was showing up in this form that we wrote down over here on the left side. So where does this equation come from? Honestly, it was somebody way smarter than me, and way before I was ever around, figured out that if we use this equation that changes the u in terms of y or the y in terms of u, we will get a nice result from this. Namely, I'm going to write down another equation here. This is also something you're going to want to learn. U prime plus 1 minus n times p of x times u equals 1 minus n times q of x. That also deserves to be into a box. That is the new equation that we end up with. Okay? So the diehards out there are probably already wondering, how do I take this Bernoulli equation and use this change of variables and somehow end up with this? Right? Totally reasonable question. And I'm not the type of guy normally, guys, you will not see me very often just sort of throwing an equation out at you. I usually like to explain everything that you see. It turns out that this explanation isn't really critical for the flow of the class and what you guys really need to know. So what I actually did is I made a little video about it. And it's not going to be a required video. It's kind of an optional video that I made. And I think I'm going to show you in a little while where it is at. But let me just put in parentheses here, for those of you diehards that would really like to understand where does this new equation come from if I implement that change of variables, I have a very short video explaining that. But you don't need to worry about it unless it's of interest to you. What you do need to worry about is that you know these three equations in the boxes down here. You need to know what a Bernoulli equation looks like. You need to know the change of variables formula. And you need to know what you end up with after you implement that change of variables. This equation may not look a whole lot nicer than the one we started with. In fact, it looks a little bit messier, but I need to point something out here, guys. The P of x that we started with has now picked up a 1 minus n in front of it. The key thing about that I want to make sure you're aware of, though, is that 1 minus n is just a number, right? N is a number and 1 minus n is just a number. So this is not really a big change. You're taking the P of x and throwing a constant in front of it. That's all. Same thing on the right-hand side. There's a Q of x and you're throwing a number in front of it. Not a big fundamental change to what you have there. But what you don't have in this box is a power of u on the right side. So this y to the n that we started with vanishes in this new differential equation. This right-hand side is literally just q of x with a number in front of it, which means, my friends, that this guy is linear. Oh, that's what I promised, right? I promised you that a Bernoulli equation would always become linear. And that is absolutely true. And of course, we know how to solve linear differential equations already. We watched the videos, right? So we already kind of know how that works. I would like to, if there's no questions, I would like to show you an example of this. Is everybody okay so far? Okay, sweet. Let me give myself a little room. It's going to take a minute to erase this. Like I said, it's a little chilly down here, but I'm going to get some space here cleared off. Actually, you know what's even worse than cold weather? I found this out last semester. Somebody threw some water on the board in my classroom like halfway through the semester, and they spent the rest of the semester trying to get the board to be erasable again. So don't ever throw water on a whiteboard. Not good for the whiteboard. Anyway, oh, I shouldn't have erased this this Bernoulli equation here. Sorry. Well, let me just put it right back up here again. Y prime plus P of x times y equals Q of x times y to the n. So this is my Bernoulli equation, right? Hopefully that's all visible to everybody. Okay, so let's do an example. Let's practice this for a minute. Let's try to solve the following equation. I'm going to do y prime plus 2x divided by 1 plus x squared times y. And on the right-hand side, I have xy squared. Okay, so there's my example. Okay. So of course we should go through the mental exercise. Are we sure this is not separable? Are we sure it's not linear? Right? You don't want to just assume always that it's going to have a particular form. But you can see here that there is a y squared on the right side. It actually lines up quite nicely with the form that I recopied right above, right? So this is Bernoulli. And I want to fast forward with you guys for a minute to about a month from now, when you're going to take a test, your first exam in this class, about a month from now. And if you get a question and you're like, yeah, I don't know how to solve this, but I do know that it's Bernoulli, I can recognize that much, then just to give you some advice right now for your exams, because I am a partial credit guy, if you know anything relevant towards solving this problem, even if you don't know how to do the whole thing, you should write it down, because I can give you points for knowing those things. So I would probably start off, for the solution, I would just try to identify what it is. And in this case, it is Bernoulli. And if you just write that down, I'll be able to give you some credit for knowing that. So that is Bernoulli. And if you want even a little bit more credit, you can get even more credit if you tell me what the N value is. You guys have your chat boxes open over there on your computers? Can you do me a favor? Can you open your chat box and type in a number? I want to know what is the N value for this equation. And go ahead and send it to everyone. Let's make sure we're all getting the same answer here. This is my way of making sure everybody's awake. I'll get a bunch of answers in here. Okay, I don't see any inconsistencies here at all. Everybody's got N equal to 2. That's just this number right here on that y squared. So that's really good. So we write down Bernoulli with N equals 2. Let me write down what my change of variables equation would then be, right? So then this means that U, which is equal to y to the 1 minus N. Again, this is given, right? If anybody's wondering, where does this equation come from? Is basically whoever figured out this theory has learned that this change of variables is what will work, okay? So that means we have y to the 1 minus 2. 1 minus 2 is -1. If I take y to the -1 power, I hope you guys would agree with me that that's the same as 1 over y. Okay, so the u and the y, they are just reciprocals of each other, okay? Now what I would like to do, so I've taken care of writing down the change of variables. I now want to write down this box, the big equation here at the bottom. So what we will get is, let's just put it here, we get u prime. And then, what does this say here? 1 minus n. A 1 minus 2 is -1. So there's a minus sign that's going to go in front of the p of x. By the way, p of x is right here. This is p of x, yeah? By the way, q of x is just x. It's right there. Those are matching up perfectly. So the p of x has to be appended with a minus sign here, 1 minus 2. So this becomes minus 2 over x, sorry, 2x over 1 plus x squared. And that's now times u. And then on the right-hand side of the equal sign where I have 1 minus 2, that's just a minus in front of the q of x, which was x. So this is the new equation that we have. And if I'm going too fast here, guys, just get my attention here. You can certainly ask a question or just ask me to slow down for a minute. This equation should be, if I'm correct in this whole theory that I've been trying to describe, it should be linear now. You notice there's no u to the n over here, right? The right-hand side just has x as the only variable that we see. So that's a good sign. So this is a good chance to review how to solve linear equations. By the way, I really like the Bernoulli differential equations. Right, Audrey? She's nodding.
Yes, sir.
She took my final exam not that long ago. She knows that I put these on my finals. Why do I do that? Well, it's because it's a great chance to review not only this change of variables technique, which is a powerful process, but also to review how to solve linear differential equations too. It's something we all want to be able to do after a class like this. So let's remember that to do this, we have to use the integrating factor. So that's the I of x. I've still got it on the board, actually. I of x is e raised to the integral of, now this says p of x. Let me just be clear that we're talking about the p of x for this new differential equation, not the original p of x from the start of the problem, right? So in this case, we do have a minus sign, and that does need to be included. That does need to be included as part of the p of x. So if there's a sign, a minus sign there, don't forget about it. It does need to be included. So this is the integral that we have to do. And let's just spend a minute and work this out. This is just e to the minus. I'll pull out the minus sign. If I look at the rest of that integral though, you guys see this thing here, 2x over 1 plus x squared? That would be a fraction that we could integrate by using what? U sub, yeah, U substitution, right? I can just make the denominator into the 1 plus, and by the way, it's not the same U that we're talking about now, but it's basically what you would have learned in your calculus class, right? I would let U equal 1 plus x squared. The du for that is just 2x dx, which is exactly what's on top. If I integrate 1 over U du, I just get the natural log of the absolute value of U. I'm not going to put those absolute value bars on this though, because 1 plus x squared is already positive, right? So you would just get something that looks kind of like that. Do I need to put a plus C on this integrating factor? Do you guys remember from my video? You don't need to do that, right? We're only looking for one integrating factor. We don't have to find like the whole family of all of them. So I might as well just choose C to be 0, make my life easy. And I'm just going to use this integrating factor like so. Of course, I would like to cancel the E with the ln. Those are like inverse functions that cancel one another out. But there is a minus sign that is in the way here. So I'm just going to review this high school algebra with you for just a moment. I'm going to take that minus sign, and the way it works with logarithms is we can throw it upstairs as an exponent, right? We can put it up on top here. So this minus sign is like a -1. It goes inside as an exponent. And that allows me to cancel the E with the ln. That's what I want to do. And at this point, you literally just have the reciprocal of 1 plus x squared. You have a -1 power on the 1 plus x squared. So that is your integrating factor. Okay, looking good so far. I find that even in this class, sometimes people are having a little bit of trouble with that step with the logarithm. So it's something I want to try to be careful to review, especially early in the semester here, this thing about taking that coefficient and throwing it upstairs as a power. It's a pretty important property of logarithms. So that's what we've done right there. And then we just have to remember from the videos what we do next, right? What we have to do now is take the product rule of the integrating factor with the unknown function. So this is going to be the derivative of the product of I times U, right? Right now, the unknown function is U. And so that should be equal to the Q of X times the integrating factor. So that's going to be -x divided by 1 plus x squared. Okay, so if I just erased it, I didn't mean to do that so quickly, but normally what you would have had, and this was what you saw in my videos, is this is what you can do with your integrating factor, right? You basically take the derivative of the product of the integrating factor with your unknown function, and you set it equal to Q of X times I. The only difference now is my unknown function here is U instead of Y. Right, okay. So far, so good? Any questions so far? We're almost done. I know this takes a little while to go all the way through all of this. Okay, the only thing left to do now is integrate both sides. Right, so I'm now going to, I'll do this up here. I'm going to integrate on both sides. So when I do that on the left side, I actually will cancel out the derivative. So I'll have 1 over 1 plus x squared times U. And then on the right-hand side, I have to integrate this thing down here, guys. Now, this thing here is actually very similar to the thing that we integrated earlier when we were doing the integrating factor. What I need to do with this one, though, you might notice here, I want to do that same U substitution again. I want to do the same U substitution with U equal to 1 plus x squared. The du for that would have been 2x. Well, I don't have a 2 there. So what I can do is I can put a 2 in. I'm going to go ahead and do it right here. I can put a 2 in on the top and on the bottom. And the 2 that's on the top, right, can be combined with that x to make 2x. Just reviewing U substitution here. I still have a minus sign, and I now have an extra factor of 2 on the bottom. So this is going to result in a -1/2. And then other than that, the integral is the same as before. I just have to integrate du over u, and that's just gonna give me the ln of 1 plus x squared again. This time, however, I do need the plus c. At this point, I am going for the general solution. I'm trying to get all of the family of solutions to my differential equation. So I definitely need the plus c here, and that would be the result of the integration on the right side. Is everybody with me? Am I done? Is that going to be the final answer? Fadi, I see you shaking your head no. What's wrong?
Yeah, we just need to divide by I one more time for both
Okay,
sides.
exactly. I need to isolate this u that I have. And so to do that, I need to divide by the I, the integrating factor, which in this case just amounts to multiplying through by 1 plus x squared. So I'm going to go ahead and do that. Let's use some big boy brackets here, though, on the right side to really keep this clear. I'm going to use some big brackets over there. I've got my 1 plus x squared, and then the rest of it in parentheses. Okay, so those parentheses are really your friend here. All right. Incidentally, is it okay for me to move this plus c to the outside and just tack it on the very end, or do I need to leave it the way it is? I only bring it up because I see people do it all the time. You better leave it. Yeah, Fadi's got it. You better leave it the way it is. Don't try to get fancy with the plus C and just toss it out on the end. It needs to be inside of that bracketed part there on the right-hand side. Okay, so that's what we have so far. Is that the final answer now? Tell you what, in your chat box, can you type either yes or no? I want to get everybody's input on this. Do you guys think, is this the final answer to this problem? Yes or no? I see some yeses. I see a yes that turned into a no. I see a lot more no's than yes. Okay, so for all of you who are saying no, I want to know what's wrong. Why is this not the final answer? What do I need to do? You can type or you can use your microphone, either way. Okay. Jackson, Daniel, yeah, the U is the issue, right? We're not looking for U, we're looking for Y, right? If we go back to the original problem up here, we were solving for Y. So what I have right here is the solution for U, but I need to figure out what Y is. And you can see, how am I going to figure out what Y is? It's right here, guys. Sorry, I know it's easy to lose things on this board, but right here, the U and the Y, they are reciprocals of each other. So if I want to figure out what Y is, so I can actually think of U as being 1 over Y right here. And so now if I want to get Y by itself, I would just have to flip everything over. So this is going to be a big 1 over everything. Right, so we have a numerator of a 1. And then the denominator is exactly this whole thing that we had written down before, like so. This would be a final answer, and we certainly can put a nice box around that. Okay, what do you guys think? Is this clear enough? Just don't forget that last step where you go back in terms of Y again. That's the whole reason you need to write down this change of variables. Okay, good. So far, so good? All right, so that was one type of change of variables, right? We can take a Bernoulli differential equation, and I've given you some tools here. These boxed equations are really the key to the whole thing. These boxed equations will allow you to convert this into a linear differential equation and then solve it from there. And we've now seen a nice example of that. By the way, you won't actually have any homework on this until next week. So you got a few days to kind of let this sink in a little bit. Certainly can ask me questions as you're starting to try to work some problems out for yourself. But it's a nice technique. It's a good one to learn. I mentioned that there's a second type of change of variables that's relatively useful as well, and that was something called homogeneous differential equations of degree zero. I'd like to show that to you as well, but I think we're about an hour into the class right now, just roughly an hour in, somewhere usually in the middle of class. I like to give people a little break. And so this is kind of a nice little stopping point. I think I'm going to take 10 minutes now and let you guys, I don't know, stretch your legs, get some water, just kind of break from the screen, if you will. And at about 7:10, we'll pick things back up, and I'm going to go over that second type of change of variables. Okay, so go ahead if you want. You can step away for about 10 minutes or so, and then we'll finish up the second part of the class. During the break, by the way, guys, sorry. If you have questions on the homework that's due tomorrow night, feel free to type some question numbers into the chat for me. And that way I'll kind of know if people have things they want me to go over. I'll try to save a little time for that. Okay, I'll see you in 10 minutes. 45 minutes? Okay. All right. Okay, well, I'll see you tomorrow. Hey guys, if you're out there somewhere within the sound of my voice, I'm gonna start up again in about 1 more minute. So if you're close by, this would be a great time to kind of get refocused in here. And yeah, we'll start up here briefly in a moment. All right. Well, if I could get everybody back over here again, if you have a webcam that you can turn on, I see a few faces out there, but not as quite as many as I'd like. I know it's not always doable, but it's really appreciated if you're able to get your cameras on. That's really helpful. Thank you. Yeah, so let's go ahead and pick things back up. Before I go over this second half of our class today, I wanted to just show you something. I'm going to share my screen for a minute and show you where to find something on our Canvas page. So I'm hoping that this is working and that you're going to see a nice picture of the homepage of our Canvas class here. I just wanted to show you, if we go over to the pages section, right, this is where I'm kind of keeping track of videos. So you see, for example, class lectures. I don't know if you know this, I'm recording this lecture right now. And later on tonight, I will take this lecture and make a YouTube video into it. And then I'll provide a link to you in this class lectures folder. The other thing was there's a link here to some additional videos. And I just wanted to show you this. You don't need to look into this folder unless I ask you to. And I just wanted to point out that, you know, we're currently going over section 1.8, and here's that video. I just was going to show you. This is this little video that I made about converting a Bernoulli equation into a linear one. It's only a 3-minute video, but if you're interested in that, I know some of you diehards out there might actually want to find that video and just watch it and make sure that you are up to par with how that works, but it's not required. I'm not gonna make you guys watch that video if you don't want to. It's just for those of you who are interested. Yeah, so from time to time, I might reference you over to a video in that compilation. There will be some more required videos as well from time to time throughout the semester, but not this particular one. I think I'll just let that be optional for now. But yeah, I think if we're all good out there, I'm going to continue here with this second example of a differential equation that we can solve by change of variables. So we've already learned that a Bernoulli differential equation is very similar to a linear one, and we can just do the process I showed you before the break to make that conversion and solve those kinds of differential equations. I want to show you one more of these kinds of possible scenarios, and that is homogeneous differential equations of degree 0. So I mentioned this just a brief moment ago, and now I'd like to try to show this to you. So I'm starting to write the definition up here for you, and now I'm going to do it. If we want to identify a homogeneous differential equation of degree 0, what we need to do is isolate the derivative of the unknown function first. So we would solve for y prime, right, and have it on the left side. And then on the right-hand side of this equation, we should have some function, and I'm writing it here as f of x and y. This is just some mishmash of x's and y's in some kind of a 2-variable function. Could be anything, right? However, in order to be homogeneous of degree 0, there's an extra requirement on this function f of x and y. Namely, that if we take every single x that is in our function and change it to xt, and then we take every single y that is in our function and we change it to yt. So if we go through this seemingly silly exercise of changing all the x's to xt and changing all the y's to yt, and if that new function is actually the same as what we had before, in other words, the t's just cancel out, then the equation is homogeneous of degree 0. That's the definition. Okay, so the hardest part about the change of variables for this is actually pretty easy. The hard part about this case B here is just understanding what this means right here. And so I want to do a couple of examples to explain it. It's actually not that hard, but I do think it's worth a moment to look at a couple of examples. So EX, I'm going to do an example here. Let's suppose that my f of x and y was equal to the fraction 3x divided by 5y plus 2. Okay, so I'm going to take this as an example. And the question I want to ask is whether it's homogeneous or not. I'm actually going to ask it and answer it right away. Turns out this is not homogeneous of degree 0. And I would like to show you why it is not. Okay. What I'm going to do to convince you of this is I'm going to look at f of xt and yt. Now, what does this mean again? This just means that in the formula for f that I was given in this example, I'm going to take every place that I have an x, and I'm gonna write it as x times t. And everywhere I see a y, I'm gonna write it as y times t. So in this case, it would become 3xt divided by 5yt plus 2. And my question for you is that the same? Is that the same as the original f of x and y? I see people shaking their head no, and I'm really happy about that because it is not, right? The algebra is not going to allow us to just cancel these t's. That 2 that is added there on the bottom right, that's actually what's getting this thing into trouble, right? Because we can't factor a t out of the denominator to cancel it with the numerator. So in this case, this is not the same thing as the original f of x and y, right? So this one was f of x and y without the t's in it. And so it's kind of a little algebra exercise. Can you cancel out the t's? Here the answer is no. It does not work, and so this is not homogeneous, which means we're not talking about it in this section, okay? Let's try one more example, just to show you kind of the opposite situation. Let's look at this example, f of x and y equals, I'm gonna use another fraction this time. But this time my fraction is going to be x squared minus xy plus 2y squared, all divided by 2x squared plus 3y squared. Okay, so this is a fraction consisting of sort of two polynomial functions of x's and y's. And I claim that this one is homogeneous. This is homogeneous of degree 0. And I, again, would like to show you the math that justifies that. Okay, so I'm going to also show you the math on this. Okay, so let's do that here. I'm going to write f of xt comma yt, and I'm going to make this fraction for you. All right, let me know if you're having any trouble reading anything here, by the way. Just trying to use my space here wisely. I have x squared. Well, now I'm going to write that as the quantity xt squared. So everywhere I see an x, now I'm writing it as xt. And then I have minus xy, but that's going to become xt yt. And then finally I have plus 2 times, well, the y squared turns into yt quantity squared. Okay? So everywhere I have an x, now it's xt. Everywhere I have a y, now it's yt. I'm going to do the same thing in the denominator. So the denominator has a 2, and then I have x squared, which becomes xt, quantity squared. And then I have plus 3 times yt, quantity squared. So it's a little bit cumbersome writing it out, but what we're looking for here is whether we can cancel the t's or not. That's the main issue. That's what this definition up here is saying. Can you take f of xt and yt and replace it back with f of x and y again? Is it the same as what you started with? What do you guys think? Is there any algebra that you might propose here that could help us to check this? I see a lot of t's on the top, and I also see a lot of t's on the bottom. In every term, there's some t's, aren't there? Yeah, Fadi's pointed it out for us in the chat, right? There's a t squared everywhere in all of these terms. So I could actually pull a t squared out of the numerator because everywhere in the top there is 2 factors of t. That'll leave me with an x squared here minus xy and then plus 2y squared. So I just pull that t squared right out of the numerator. And you know what? I can do exactly the same thing in the denominator. Sorry, I'll pull this down a little bit. I can see that maybe it's hard to see that one screen there. So I'm gonna do the same thing, guys, in the denominator. I'm gonna pull out a t squared. Right? Hopefully this is all readable. And that leaves me with 2x squared plus 3y squared. How about that? So I've just factored as many t's out, and somebody in my first class asked me, is there any like easier way to figure this out? The intuition here is that every single term on the top and the bottom has the same weight, right? There's, two x's, and then there's one x and one y, and then there's two y's. And everything has a weight of 2. And that's why we're getting 2 factors of t pulling out of everywhere on the top and on the bottom. And I can cancel them. And the cancellation is what allows me to say, yep, that's still equal to f of x and y. All right, so we end up back with the same function that we started with. We've kind of done this silly little exercise where I have inserted t's with every single expression on top and bottom, and I've managed to factor them out and cancel them. So this would be homogeneous of degree 0. Questions on this so far? I have not yet explained how we actually solve one of these. I just want us to be able to understand what they're going to look like and like how to test if your differential equation really is homogeneous of degree 0. What I'm going to do now is give you the method. It's a change of variables again, right? So for this situation, which is B, for B, we are going to use the change of variables and it's not the same change of variables that we had for the Bernoulli equations earlier. This is going to be different. And I'm going to actually use a different letter so that we don't mix these two techniques up. I'm actually going to use a V instead of a U. And here is the change of variables. Again, I did not come up with this myself. This was part of the theory way before I was born. And somebody really clever and smart sort of pulled this out of the sky and figured out that this is going to work. Let's see actually what's going to happen. I'm writing V as y over x, but it turns out that it's more useful to write it a little bit differently. And I'm going to do that right here for you. That is, we can actually rewrite y as x times v. So if you just kind of solve this equation for y, you get y equals x times v. And I can see from my differential equation, here's the differential equation, guys, right here. This is what you're really trying to solve. And I can see here that I want to know, I'm going to need to know what y prime is as well in terms of doing this change of variables. So I'm going to write down y prime as well. It's might as well get it in the notes now because we do need this as well. And the way this is going to look, guys, I want to take the derivative of x times v. I want to take the derivative of that. So that, well, the thing is that that just required the product rule. So I can do that just with the product rule here. And the product rule would just tell me first term times the derivative of the second plus the second term times the derivative of the first. So that would be x times v prime plus v times x prime, but x prime is just 1. So there you go. This is really what is the most useful. What I put into the box there, the formulas for y and for y prime. And I promise you that if you implement that change of variables on a homogeneous differential equation of degree 0, it will always make it separable. It will always become a separable equation. So what I'd like to do is an example of that, just to show you how this works. Before I do that though, are there any questions so far? I've still got my chat box open here, so if I'm not making sense or we need any clarification, don't hesitate. Oh, this will be so much easier in a couple of weeks. Okay, so in the meantime, let's try an example of this, okay? I want to practice one of these. So here's an example that we could do. Let's solve the following differential equation. I'm gonna call it y prime equals y over x plus the square root of the quantity 16x² minus y² all over x. So there's a problem for us to practice on. Now I know that I'm talking about homogeneous differential equations of degree 0. So you're all sitting there thinking, oh, this must be homogeneous of degree 0. You're right. But guys, we need to get in the habit, because on the exam, it's not going to say, oh, by the way, this is homogeneous of degree 0, right? You're going to have to be able to go through a process of analyzing these differential equations and asking yourself, this is one of the skills I want everybody to get in chapter 1, is to look at this and say, is this separable? Is it linear? And as of tonight, we can now ask, is it Bernoulli? And is it homogeneous at degree 0? We now have 4 different types of equations. This is the last one. I promise we're not going beyond 4. But we are going to have to be able to distinguish these things. So I can see, for example, that I'm never going to extract an x² minus y² from a radical. I have a square root here. There's no algebra on this earth that I'm aware of that would allow me to kind of like pull the x's and y's onto opposite sides of the equal sign if they're sitting underneath a radical with a minus sign. That's just not going to happen, right? I also know that this is not linear because I see a y² right off the bat, it's game over, right? If you see a y², it's not linear. It doesn't have the right form. Linear equations cannot have powers of y in them. Just doesn't work, right? And it's not even Bernoulli. I know Bernoulli equations are allowed to have powers of y, but they have to be outside by themselves, kind of multiplied by some q of x. And that's not the way that we see this y² right here. So this whole second term is really problematic. It's not going to allow it to be separable or linear or Bernoulli. And almost by process of elimination, the only other choice would be homogeneous of degree 0. And so if we think of that as the f of x and y, I won't take the time right now, but if you were to attach a t, like we were doing over here, if you were to attach a t next to every single x and every single y on the top and the bottom of both terms, right, you could show that they will cancel out. You can even see it right here, y over x, that's going to turn into yt over xt. Those t's are going to cancel immediately. And you'll also have cancellation of the t's on the right-hand side. It's a little bit more work algebraically, but it's certainly gonna happen. Fadi's asking, if I can just see it right away on the test that it's homogeneous at degree 0, do I have to show all the work or the proof for that? I'm usually okay with people, being able to observe things, and sometimes it will be rather obvious. Usually my rule of thumb is if it's not obvious to me, and I've been doing this for 30 semesters of teaching, right, is probably not going to be obvious to anybody else too quickly. So I would rather see some work shown. It's a little bit of a judgment call. Generally, I'm okay if I imagine that, yeah, the student might have been able to figure that out in their head with a little mental arithmetic. I can usually live with that. Okay, so, but it's a tough call. Anyway, in this case, it is homogeneous of degree 0, so I'm going to implement the boxed change of variables here to solve it. So let's get into the solution here. So all I'm saying here, guys, is you can check. I'm not going to do it, but you can check that this is in fact homogeneous. You can check that. I'll leave that for you guys if you're interested. But this one is homogeneous. Notice on the left side, all I have is y prime. So that y prime needs to be rewritten as x v prime plus v. And then on the right-hand side of the equal sign, you'll notice I have y divided by x. Well, that just becomes v immediately, right? And then on the second term, I still have this fraction. It's a little messy. the square root of 16x² minus, now I'm gonna change the variables. The y squared can be rewritten as x² v², right? I can change the y to xv like so. Okay? Now my promise to you was that this is gonna make it separable. Well, let's see if we can get there. I can cancel a v on both sides of the equal sign. That kind of helps out a little bit. And then, can you guys all see on this last term over here that there's an x² that can be factored underneath that square root? Yeah. I can factor this x². If I do that and then yank it out of the radical, it's gonna cancel the x that's on the bottom. It's actually gonna cancel the x that's on the bottom. So actually what's going to happen is this is simply going to become the square root of 16 minus v². Pretty nice. Pretty nice. And the v prime that you see there, I'm gonna rewrite this. I think in my video on separable differential equations, I probably I encouraged you when you're separating things to rewrite your derivatives using the Leibniz notation, the dv over the dx here. That's just gonna make it a little bit easier to see how to separate it. I'll leave the right-hand side the same for the moment. And now I think we're pretty close, right? We're pretty close to having this thing separated. I'm gonna go ahead and I'm gonna divide the radical 16 minus v² underneath the dv. And then the other thing I'm gonna do is, you see the x, the dx here, I'm gonna kind of like flip those over to the opposite side of the equal sign here. So we'll end up with a dx over x, like so. Yeah. How's that looking? Fabiola has a question. So the x is outside of the radical.
The 1 over x? Sorry.
I'm sorry?
The 1 over x, right?
Yeah, this x on the bottom is not part of the radical.
Okay.
That's totally in the denominator. That's a really good question.
Okay, thank you.
You're right. And Tien, I see your comment in the chat also, which is actually a really good one, which is that when I pulled this x² out of the radical, so effectively I was taking the square root of x², I should have put I should have put the absolute value of x there. That just makes my life complicated right now. So I'm going to assume that x is greater than 0. So we'll just, I probably should have just added that into this question. Actually, the truth of the matter is, assuming that x is greater than 0 here is reasonable. If x was equal to 0, you would be taking the square root of negative something squared. That's not gonna make a lot of sense. So it's pretty reasonable to just make sense out of this problem by having x positive, in which case we don't need those absolute value bars. I hope that's a satisfactory answer for now anyway. Yeah, but these are all good points. You guys are bringing up some good points. Let me just get this arrow kind of out of my way here. Yeah, so this is my separated differential equation, guys. And we solve that by integrating both sides, right? We solve that by integrating both sides. So let me give myself some room over here to get the results coming out. Yeah, so we're just about done. Thanks for hanging in there with me tonight, guys. I know it's been kind of a long session in front of a screen. And this will not last for more than a couple of weeks. Okay, so I now want to integrate both sides of this. Yeah, and to do that, I'll start with the right-hand side. The integral of 1 over x dx, I'm hoping everybody has that one like down pat. That's just the ln of absolute x plus c. Again, if we were assuming x is positive, I wouldn't need the absolute value bars, but I'll go ahead and leave them in for the time being. On the left side, we have an integral that I would not actually expect you guys to sort of know off the top of your head. I'm going to be giving you a table of integrals. for any exam in this class. It's actually in Canvas already. If you want to look in the files section, I've got it in there somewhere. This one would be in your table of integrals. I'm just going to spit it out what it would be right now for you. It's going to be an arc sine of v over 4. So this is from a table. This is from a table. So make sure you guys can read that whole thing. This would be from an integration table. So don't worry too much about that. So that's the integral on both sides. And notice that I did put the plus c on the right-hand side, which I need to do here. Okay, am I done, by the way? Is this it? What else do I need to do, guys? Somebody help me out. You can use your microphone, you can type something in the chat. I'm looking at everything. I'm looking for help. What do I do at this point? This is not the final answer. There's actually two things wrong with it.
So we need to resubstitute v for y again.
Okay, yeah, we need to replace the v. Cody's got it, Derek's got it in the chat. We need to replace this v back in terms of x and y again. We know how to do it. It's right here, right? V just gets replaced by y over x. So let's just do that as a first step. So this is going to become the arc sine. This is an inverse sine function, guys, right? And so this just becomes y over x. And so I've got y over 4x inside those parentheses. Right-hand side pretty much stays the same for the time being as such, okay? So that's one thing. Now we got rid of the v and replaced it in terms of the original variables. Is there anything else that we should do before we kind of call it good? Yeah, this is not a wrong answer. Well, what's up here is actually totally correct. It's just that this would be what's called an implicit solution. And I'm okay with an implicit solution if it's not possible to solve for y. But as Cody is pointing out in the chat, we definitely can solve this one for y. It's just a little bit of algebra that we have to do. Since I have an arc sine on the left side, I can move that out of the way by applying the sine on both sides. So I can get rid of that arc sine by just moving the sine to the opposite side. Remember, the sine is an inverse function. The arc sine and the sine are inverse functions. So if I take the sine of the arc sine of blob, I just get that same blob back again. And so this is a good way to try to isolate the y. And at this point, we can easily just get y by itself. I'll just move the 4x over. And so I'll have 4x times the sine of the quantity of the ln of absolute x plus c. Just as I pointed out in the earlier example, please don't get careless with that plus c. It should not just dangle off on the end of this expression. It does need to be inside of those parentheses. The parentheses are going to be your friend on this stuff, guys. And generally, I don't expect people to do a lot of algebraic simplification of their work. But if you do simplify it and you simplify it wrong, then I'm not going to be so happy about it. Meaning my red pen is going to come out. So it's almost better to not, if you're not sure, it's almost better to just leave it the way you find it. And that should be fine. Okay, so this would be a great final answer. It's an explicit solution for y. Of course, if I had initial values, this would be the place where we would take those initial values and we could plug in an initial value for x and for y and solve for c to get a particular solution. So kind of going back to some of the stuff from the videos, this is called the general solution to the differential equation, but I could get the particular solution that goes with an initial condition if I had that information. So I could plug that in and solve for c. Okay, but that's not something we need to do on this example. All right, are there any questions about this section B here? This is the change of variables for a homogeneous differential equation of degree 0. It'll definitely take a little practice. One thing you're going to want to practice sooner than later is just making sure that you can identify whether something is separable, linear, Bernoulli, or homogeneous, right? These 4 types of equations. On Tuesday next week, I'll probably pull up a group work from my Canvas page, and we'll actually do a little exercise to practice that. But I want to give you the weekend to kind of let that sink in a little bit, try to get a little bit more comfortable with these new differential equations. Speaking of Tuesday, on Tuesday, we will actually be starting chapter 2. So you're going to come in here and it's going to be a very different class. I'll be talking about matrices and systems of equations and how to solve systems and stuff like that. So that's going to be something to look forward to all weekend long. What I'd like to do with the 8 minutes that apparently I have left for tonight is help you guys with the homework that's due tomorrow night. There was one problem that somebody put into the chat earlier, and I've got to pull it up here on my side. I actually don't have my book with me. So I'm going to do number 31, I think it was, from, I think it's from section 1.1. Actually, I'm not sure which section this is. This might be 1.2, actually. So I just have to pull it up on my side so that I can see it. Yeah, so I'm going to do this problem. It is actually from section 1.2. Number 31 for you, or at least I'm going to get you started on it with whatever time I have time to get into. And so this is what you're doing on number 31. They give you a differential equation. Let me see if I can copy it down correctly. Here it is, y prime equals, and then it's just this horrendous fraction. And it's got x squared in the numerator times 1 minus y squared. And then it has plus y times e to the y over x, okay? And then in the denominator, there is an x, and then there's the quantity e to the y over x plus 2x squared y. Okay, so they give us that differential equation, guys. And what they, of course, we don't know how to solve it. This one is crazy messy. It's not like we would want to solve this ourselves. But there's good news here, which is that instead of making us solve this differential equation, the book actually gives us the answer and just asks us to verify the answer. So the answer is, I'm going to write the answer here. Again, I'm just copying this out of the book from the question. E to the y over x power plus xy squared minus x equals c. That, as it turns out, that is what the answer is supposed to be. Okay, so let me explain how you're going to do this problem in case you're feeling a little overwhelmed by that, because it is pretty messy. By the way, guys, my grader will only grade the problems that were required on the assignment. There's also some recommended ones. That's really for people who maybe need a little extra practice. If you think that you're not getting it very well the first time through, a little extra practice can go a long way. So I put some recommended problems down there, but you don't have to do those. This one, what it really is, guys, let me just give you in a nutshell what this problem is asking you to do. They're just asking you to take this equation, which admittedly is implicit, right? I don't have this solved for y, nor would I be able to very easily solve it for y. So this is an implicit equation. They just want to know, or they just want to show that this does solve the differential equation. And to do that, we really just need to figure out what is the y prime for this curve. This is a curve in the xy plane, right? This is just some curve. I just need to figure out what is y prime for that curve and make sure that it agrees with what the differential equation says that the y prime is for that curve. So the solution here, and again, this is just, I'm happy to do homework for you guys whenever we have time. The solution for this is literally to just take the derivative of this and just make sure that it matches what y prime is supposed to be equal. The tricky part is this curve is implicit, which means we're going to need to do implicit differentiation. It's not something that you do as often in calculus. And so sometimes I think people get a little bit thrown off by it because they just haven't seen this kind of a thing that often. I'm gonna go ahead and sort of show you at least the start of this. We've got about 5 minutes. We should be able to get through most of it actually. I'm just gonna take the derivative. So I'm gonna take the implicit derivative of the curve. Okay, so that's what I'm gonna do. And let's just see if we can get to the answer. I'm gonna start with the easy stuff. On the right-hand side, the derivative of a constant is, what's that gonna be equal to? It's 0, right? It's just a 0 on the right-hand side. The derivative of a constant is 0. What is the derivative of x? Well, that would be 1. So I'm gonna put -1 there. I'm kind of working from right to left. What about the xy squared part? Now, when I take the derivative of xy squared, I have to recognize that that is a product that I am taking the derivative of. And to do such a thing, we would use the product rule, right? So I'm going to use the product rule. I'm going to grab some brackets here. I'm going to grab some brackets and I'm going to do the first term, which is x, times the derivative of the second part. The derivative of y squared. Well, normally the derivative of x squared would have been 2x, but the derivative of y squared is actually 2y times y prime. I have to use that chain rule, right? This is how the implicit differentiation gets a little quirky. When you differentiate x, you just get 1, but when you differentiate y, you just get y prime. So it's not exactly handled in the same way. And then the second part of the product rule is the second term, which is y squared times the derivative of x, but the derivative of x is just 1. So that's my derivative of this term. And then what about the first part? And I don't know if I have enough room here. I'll put a little arrow here. This is e raised to the blob, right? That we all know that the derivative of e to the x is just e to the x. But when I have a blob there, and then when I take the derivative of e to the blob, I get e to the blob times the derivative of this blob. So in this case, I have to take the derivative of y over x. Y over x, of course, is a quotient. So I would need to use the quotient rule to take the derivative of y over x. The quotient rule has a low squared on the bottom, so the x squared would be on the bottom there. And then, what's the old mnemonic for this? Low d high minus high d low, right? So the low is x, the derivative of the high is y prime, minus the high, which is y, times the derivative of the low, which is just 1. So that would be it. Okay, and then I still have all this other stuff here. And I'm gonna get saved by the bell because we're just about out of time. But what you need to do now is solve this for y prime. It looks bad, but it's actually not as bad as you might think. You have a y prime here and here. So you'll have to do a little bit of algebra to kind of get the y prime terms together. And then kind of factor that y prime out in order to solve for it. So I think I will let you try to finish it from here. Of course, I am happy during office hours to kind of go through more of the details to get to the finish line with this one. But I think I've at least gotten you started on kind of how you're supposed to approach it, which I hope has been helpful. So, yeah, so that's kind of where I'll leave it, I think. Is that okay? Everybody, at least get you started. You've still got more than 24 hours to get this thing done, so there's plenty of time. Guys, we are basically right at the finishing bell here. I am going to head over to my Zoom office hours this evening, so if you did want to work with me on anything later, feel free to do that. Meanwhile, I just want to thank you all for being here tonight and to remind you that we are meeting here again, same exact place next Tuesday and Thursday also. It's not until the week after that that I'll be back in Fullerton again. Yeah, so thank you all for coming, and I look forward to seeing you again soon. And have a great night. Thanks again for being here.
Thank you.
You're welcome.
Hi, Dr. Annan.